as we transition to a more renewable dependent energy economy, we're relying more and more on the weather systems around us. So what happens when the weather doesn't actively contribute as the risk by being destructive, but rather by being inactive and not doing the things that we actually wanted to do? Surprise, surprise, wind energy comes from wind, and we need the right wind speeds for it to generate energy and turn the turbines. But as we see now, wind droughts are becoming more and more of a risk, and they directly impact how we kind of model our supply and demand for energy. So, next slide, please. As Frankie mentioned on Monday, Energy Australia has several wind farm sites. So this week we decided to focus on Cathedral Rocks, Morton's Lane, and Gullin Range. But first of all, let's zoom out a bit and kind of see how we actually define wind droughts and what the characterizations for them are.
So there's a number of ways you can define a wind drought. Quite often wind speed percentiles are used, but given this is a very energy sector stakeholder relevant project, we decided to focus on capacity factor. So the way we defined a drought is any consecutive 3-day period below a capacity factor threshold. So we've experimented a little bit with changing the threshold, which is CF here. Now, if you set the threshold to be lower, 10%, you're going to get less droughts because they're simply capturing less events. And this plot in particular looks at the duration. So, if you set the threshold lower, you're going to get shorter droughts in general because you're going to capture less more extreme events. Next slide, please. The next segment of the project, we decided to try and assess how well the reference years from the AEMO stats could capture the entire distribution of the capacity factor data we had, which goes back to the 1940s. So this is a map of frequency of droughts, so how often they occur. And you can see in some of the circled areas, there's some pretty significant differences where the more recent reference years tend to get higher or lower, or less or more droughts than the overall time series. And the focus here is that there is a difference between using the whole series and using just the last 13 years.
Now, similar to frequency, we also had a little look at our mean wind drought duration. And again, we were looking at comparing our full climatology with our reference year data set. Now, what we can see here is we do have a bit of spotty variation with our reference data set over in Western Australia as well as Central Australia. So over up there in Western Australia, what we're seeing there is a bit of an increase. And then in Central Australia, we've got a bit of both. So mainly decrease in our mean wind drought duration, but there's also some patches of increases there as well. Now, if we take a look at our maximum wind drought duration, what we're seeing pretty consistently is that when we move towards using our reference year's data set, what we're seeing is a decrease in the duration of our wind droughts. And that's happening quite consistently throughout most of Australia. And now what this shows for us is that our reference data set is generally underestimating the longer wind drought events. And this is a product of the fact that our shorter timeframes are generally more likely to be less likely to capture extreme events.
Thank you. Okay, so then we took a look at the specific sites that Energy Australia has partnership with. So the Cathedral Rocks, they have part ownership, so we looked at that first, and we looked at the frequency of wind lull events at these sites. So the blue on the graph shows the entire time frame from the 1940s to 2023. Sorry. The red is the AEMO reference years from 2010 to 2023, and then we have the average dotted lines for both, so we can see the differences. So for the Cathedral Rocks, we can see that it's actually an overestimation. The reference years compared to the average, which is more around 3, it's about like 3.2. And then with the Gullian Range, we can see kind of the opposite effect here, where the overall average for the number of events is more around the 7, and then obviously the reference years is under. And then Morton's Lane is the one that has the biggest difference here, and we can see that there's a 2-day average of the frequency of events and the fact that the reference year are overestimating, which is really interesting. Cool. And then we have our questions afterwards.
Sorry, I missed that a little bit. So are you comparing the capacity factor with the wind speed data, or what?
We didn't use any wind speed data. Mostly what we used was we looked at capacity factor,
Yes.
and we mostly compared. If you look at the capacity factor going back all the way to the 1940s
Yes.
versus just 2010 to 23, and you get all these differences. So it's really just using a longer time series. You're more likely to capture extreme events, which happen rarely.
And then what's the conclusion of all this study?
The conclusion is that it varies everywhere. You gotta do lots of testing, really uncertain. You've got to think about your reanalysis data set you're using. Like this going back to the 1940s is not real observations, it's reanalysis data. So the next group's actually going to talk more about the data you pick and how that affects it. So maybe you can combine this with theirs and then you can start making conclusions.
Oh, that's
And what was the threshold you ended up using?
0.1.
0.1, and
Yeah.
the mean length was 3 days.
So that was 3 continuous days
Yes.
where the capacity factor was below
Below
0.1 for every hour
Yeah.
of those 3 days.
Yeah.
Is that correct?
Yes.
I'm curious if you had the time series with the two averages shown.
Yeah, it's your last one.
Did you get a lower average with the longer time series? Like a lower or a higher frequency because of
Yeah, that's what the red line's showing.
Yeah, so the red line is the average for just the reference years. So we averaged that off, and then we had the average for the entire.
It's probably hard to see back there, but there's
Yeah.
this is the average for everything,
Yeah.
and then there's just a little line above here. This one's a little below, and then this one's quite a bit above. So the different areas have different.
So depending on the location,
Yes.
when you increase your time series, you either have a higher or lower.
Yeah, but in general, it's at least different.
Yeah, the point was to show that there's variation across the different site locations.
Awesome, thank you.
What about the weather data itself? How often have you seen an academic article or an industry workflow using a single data source to make grand conclusions or highly consequential real-world decisions? What if they use different data? The thing is, there are so many choices we can make about data. People use reanalysis data sets that are supposed to record past weather, but they're based on observations, but they're not truth. There are different reanalysis products available. Different products have different spatial resolutions, and we can use different time periods for our analysis. How much are the choices we're making affecting our conclusions?
Okay, so in our project, we start from compare the climatology wind draw dates across in recent 35 years across different reanalysis products. Here you can see we just follow a simple workflow. We start from the same wind drought definition based on 100-meter wind speed and based on the 20% percentile threshold and 3D persistent criteria. And we use the ER5 and the ER2 to identify the wind droughts and to calculate their statistics. Here we show the climatology wind drought dates distribution, but here we just show the difference between the ER2, use the ER2 minus the ER5. Here we can see this difference shows very clear spectral patterns. In the tropical regions, we can say ER5 tends to pick more wind drought days. But in the actual tropical regions in Australia, the ER2 tends to carry more wind drought days. That makes a real matter because for those actual tropical regions, we have more wind farms in on those land. So that means if we use the ER5 persistent use on ER5 to evaluate the wind drought in those wind farms regions, you maybe can underestimate the wind drought risks when building the wind farms. Yeah, that's to say the data set choice matters the wind drought evaluations.
Remember to go closer to the.
Now, what about spatial resolution? Suppose you want to know the wind drought probability over a large area, like a renewable energy zone. Does it matter what spatial resolution or wind data you use? Let's do a little experiment. So let's start from high resolution wind data to calculate our low resolution drought probability. There are two ways we can do this. You can first coarsen the high resolution wind data to get a low resolution, and then calculate your drought probability. Or you can calculate your drought probabilities first from the high resolution and then coarsen it. It turns out, if you go this way, you get fewer zero capacity factor days, that is, days with zero wind power production over the Great Dividing Range than you do if you go this way. But if you then change your capacity factor threshold to 10%, so the number of days with less than 10% wind power production, going this way gives you more wind drought days than going the other way. So resolution does matter. And this is in the perfect world case where the low resolution wind data is an exact averaging of the high resolution data. In the real world, low resolution data sets and high resolution data sets are structurally different. So the differences could be even larger. So in fact, we can make a stronger conclusion. Not only does resolution matter, excellent. Resolution matters even if you have perfect reanalysis data.
Okay, I'll try to hurry. So people often take this 20 percentile threshold to defining wind drought events. And similar to the group before us, we asked ourselves, what's the time period of this threshold? Does it matter, or is it just the same? And for this, we just took 3 different time periods, 5 years, 13 years, and 35 years. And from this, it looks like it doesn't really matter. Like it's almost, this basically looks very similar, but if you take the difference between the 35-year period and then the other periods, you can see that there actually are very strong differences, especially here in the northern region of Australia, compared to the 5-year difference. But then if you look at the 12-year quantile thresholds, it changes quite a lot. So this is not as strong as if you only looked at the last 5 years, but you still see differences in many regions of Australia. And that can lead to over or under prediction of wind speeds. So to conclude, it matters what type of data you choose. The resolution matters, even if you had perfect data, which oftentimes you don't. And just when picking your thresholds, be aware of the type of data or period that you pick. Thank you.
Any questions for this group? Yes.
Yes, I'm just curious, why did you choose the Barra C2? Because Barra C2 have very much high resolution, like on 4 or 5 kilometers.
Yes, so the bit that I presented about spatial resolution, that was on Barra C2. So when I said high resolution, that was Barra C2, which has 4 kilometer resolution. And I coarsened that by 6 times to 24 kilometers, which is the resolution of about R2 or EO5.
Yeah, okay, thank you.
Sorry, can you explain this?
This one.
Yeah.
So the idea was we have 2 sort of ideal data sets of different resolutions. So this is a 4 kilometer resolution, this is 24 kilometer resolution, and essentially, do we get different drought probabilities if we with different resolutions, or do we get the same? And it turns out we do actually get it. The resolution of the data you choose affects the drought probability. Either what we've done is you either or in other words, either whether you coarsen first and then calculate your drought probability, or calculate drought probability first and then coarsen, affects the result.
That was a great presentation, well done. I'm just curious on your comment. Do you think a 2% difference in probability is a big difference?
In terms of the impact on energy, I would have to probably leave that to the industry to determine. But I think the main point is this is even if you had perfect data, you would get a 2% difference. I suspect if you use low resolution and high resolution, two different models to generate those different resolutions, because those models are different, you can get even larger errors.
I guess can we bring that back to Frankie? How much of an impact would 2%? 2%. A lot. Yeah. Interesting. Okay. Last question. Yeah.
I wanted to ask about the wind speed threshold. Is that when windmills stop working, or what does that speed represent?
On this slide?
Okay,
So on this slide or one of the other?
the one, I think the first slide.
This one here, I just use 20%.
Okay, now
Melissa said, so we've heard a little bit about wind. We're now going to include solar into that. And the reason why we're looking at this is essentially wind droughts are bad, but they're especially bad when we have days like this when we also don't have solar to make up for this shortfall. Thanks. So this is an example of the type of events that we're worried about. So you can see here, this is from the winter of 1987. So here we've defined, this is our mean wind speed and a threshold that we've determined based off the 10th percentile wind capacity factors for Victoria. Same thing for solar. And we have this event where we start off with a 3-day wind lull. This gap in the middle between wind lulls is totally taken up by solar, and then we go straight back into another wind lull. And so in total we have over 20 days of very little wind and solar combined. And so it's these events that we're particularly interested in as being extremely difficult if you're relying on wind and solar during this period.
We kind of had 3 research questions for this week. So the first question was, how many years is there of significant winter time and solar and wind lulls? And then once we've figured out how many years they are, we can start picking apart the features of those combined events. And then we were going to get it into how they relate to weather regimes, but we are running out of time. And then so the data sets we used is very similar to some of the data sets the other teams have used, but including the solar capacity factor data in there, which has been produced by Doug Richardson.
Right, so what are you looking here is bottom, you get a threshold at percentile, 10th percentile. This is the solar, that one is the wind. It's a bit hard to see, but in general, here is around 8% to 20% of capacity factor. That one is around 0% to maybe around 10% of capacity factor. So the thing is, what if you use there's a debate in our table of what kind of threshold should we use? Should we use a fixed capacity factor or should we use a 10 percentile? Which one is the right one? Well, we don't know. So let's see how it goes. First this is the hourly only daytime. So hourly percentage of wind and solar lulls. and this is annual, and this one is using 10% fixed capacity factor, the other one is using 10 percentile of capacity factor. And you can see the difference here, where in like if you use like a 10%, it's more, it's not like you can't see any weather patterns, kind of. But if you use like a 10 percentile, you can see somehow it kind of like relates to the climate zones here, where you got like these tropical climate zones, you got more into the subtropics around here, and yeah, you got a Tassie, which is a different climate zones as well. So this may relate to anyone who wants to see the weather modes in relation to loss. Maybe use the percentile instead of like a fixed capacity factor if you want to relate them both, because well, in our case that we can see that there is a kind of like better connections to the capacity factor of the loss. Yeah, this is great. Thank you.
So for simplicity, we just use the flat 10% capacity factor. So a compound wind and solar drought, energy drought, is defined when at one point for a day, both the solar capacity factor and the wind capacity factor stays below 10%. So you can see the frequency on the top. So we can particularly focus on the June, July, August, which is the winter. So the frequency is higher over the Tasmania and parts of Victoria. You can see the wind duration is also higher over these regions. Yeah. And this plot shows the intensity and the maximum duration. So this signifies how long does the provider has to prepare for, let's say, if they have a battery storage. So in the worst case scenario, they have to prepare for at least 4 to 6 days in the winter, and the intensity is the severity of that compound drop.
This falls to me to wear rocket shoes. So very quickly, we've got here some kernel density estimates for the wind capacity factor against solar capacity factor. This is all year. You can see there's a bimodal distribution. Queensland has a lot of solar and not so much wind, and this is specifically in the renewable energy zones averaged for each state. However, for winter, we see that distribution changes and we get less solar, which is to be expected because it's winter. Next slide, please. And so if we then plot conditional probability of concurrent lows for solar, wind, and both wind and solar at the same time, we find that Queensland is fairly disconnected from the other states. New South Wales, Victoria, and South Australia do have some connections, particularly for solar, less so for wind. And for wind and solar, as to be expected, it's less likely than for either individually, but there's still an element of that same spatial distribution playing a factor.
All right, well, I think we can leave our summary slides up while we take questions.
Awesome.
Thank you.
I had a question about the 10th percentile, like when you're doing capacity factor threshold, and you said it's better to use 10th percentile versus a fixed rate. How do you 10th percentile of what? Is it yearly or like?
Yeah, so the two different methods that was referred to as the 10th percentile of the data distribution. So you line up all your capacity factors, taking a daily average, and so you got a distribution of capacity factors, and then your 10th percentile is 10%, or your lowest 10%, whether
So
exact threshold. And so for wind, what was the values? It was like around about 8% capacity factor for solar, like like 3% for winds, I think, depending on the region. And so that was that one. And the other one is just you set the capacity factor. Similar to what your group did, just 10% everywhere, regardless of whether you're in Tasmania or Queensland.
Okay. So it was really just so you take the percentile of the region that you're in. Is it how it works?
Yeah, so we did both. We did for the particular. That's what Fadlil was showing.
Yeah.
Whether you do it for each particular region or you just do the one for everywhere.
Cool. One more? Any?
I like your seasonal flux of combined and frequency and duration. I guess that's mainly driven by solar changes in winter time, but is there is wind doing the same thing, or what's the seasonality of the flux?
Yeah, it depends on the region. So I think in Jonathan's plots showing that Queensland has actually lower wind in the winter. You got to go to so Queensland actually is less wind in the winter. Tasmania has more. So it's a bit of a by zone thing. Do you want to make any other comment, Vikash, or on your seasonality stuff?
Actually, wind is the one that drives because we have winds all the time. I particularly think when there is no wind, that would really lead to a compound wind and solar compound crop.
Alright. Thank you, team.
Clear day and you're excited to go outside and make plans with your friends and everyone seems to be doing happy. But there seems to be someone who is very bothered by it. Frankie. So what Frankie would like is the whole cool season to be rainy and windy. This is probably what Frankie would like the whole season. So our group looked at the co-occurrences of hydrological and wind droughts in southeastern Australia. So how we define wind drought events are the days where the wind capacity factor falls below the 25th percentile, which we've calculated over the whole region. So lots of people have talked about the different ways in which they have defined the wind capacity factor, but here we have only chosen a specific value of capacity factor. So if the capacity factor falls below a certain value, it means that the generation of wind energy is low and we would need to rely on other sources of energy to compensate for that. And how we define hydrological droughts are when at each grid point, when the 12-month trailing mean of the rainfall falls below its 25th percentile. And we identify each month and check whether it's in a drought state or not. So it's a 0 or 1 value. And why that matters? It's because if there's a hydrological drought, that means the water levels in the dam are falling, and it might be difficult, especially during the cold season, to rely on hydroelectricity, which a lot of Australia depends on for energy resources. So these two are processes that occur at very different time scales. So the wind droughts are probably caused by synoptic scale systems that sit over regions, while the hydrological droughts are probably caused by the accumulation and the changes in the rainfall patterns. So we are looking at processes occurring at different time and spatial scales. So if so the figure here shows the map of Southeast Australia for the cool season, which we defined as May to October from 1940 to 2023, and the renewable energy zones for both wind and hydro, and separately are shown here in the figures. And we find the mean, for the cool season, the larger, darker red values indicate that there's more probability of the region to be in a hydrological drought. And on the figure on the right is for the wind drought events, where we've identified the wind drought events over the same cool season using daily data, and the red region shows that the southeastern part of Australia has a lot of occurrences of wind drought events. Why cool season? So cool season is when the duration of days is shorter, so we can we have more dependence on solar and wind resources, on wind and hydro and not solar. And it's especially bad when both these events occur at the same time, and it's very disadvantageous for renewable energy production.
Well, so we have already looked into the main picture for the hydrological droughts, but if you just look into that particularly cool movie, and this is exactly saying that color is saying that what is the proportion of at each grid point on that particular cool season exactly facing that drought, and you can see that yes, that main picture doesn't tell you the whole story, but if you just look into that for particularly each year, you can see that there are many regions when there are droughts happening all over the mainland Australia, but not much over Tasmania. And so at the very beginning, like on the first day that Krista mentioned that sometimes we really do some stupid things that using the mean. So I would tell that really that mean picture doesn't tell you the whole story. And also these sort of things depends on different climate modes of variability and all these sort of things. And so this plot is basically showing that like sort of area average and like the time series plot. And you can see that there are many years, in particular if you see 2019, there are much more hydrological droughts, but not much wind droughts. On the other hand, if you just look into 2010, 2022, 2023, you can see there are many more wind droughts, but not much hydrological drought. Also, if you just look at the very like 1940, we have hydrological droughts and wind droughts at the same time, like they have the higher frequency. So, so the relationship between hydrological and wind droughts are really very complex, I would say. So what we can do for the next is that we can definitely have a look into that, how much this wind and hydrological droughts actually related to the climate modes of variability, could be ENSO, maybe you can look into the SAM, then and then later we can have a look into maybe that Barnes et al. Synoptic weather typing of Australian region, and we can also have a look into that when there are maybe hydrological droughts, not much more wind droughts, or maybe when there was much more wind droughts, not hydrological droughts, and where that both co-occur, what are the different synoptic typings actually, or like synoptic scale weather actually associated with these events. We can also have a look into that if we use different thresholds or like different definition, how these sort of relationship between wind and hydrological droughts change. And also these are purely based on the weather. So basically hydrological droughts and wind droughts, we use the weather variable, but how much our results is actually supported by the energy generation. So because we expect that when there was a hydrological droughts and the wind droughts happening at the same time, there should be very, very less wind generation. So, and also we can think about that when there's not much hydrological droughts, but wind droughts, or I suppose how one can compensate each other. So there are different things we can do, and we are planning into my next. And so I would say that's it.
Thank you. Any questions? Yeah.
Can I just confirm for that time series that you were showing, that was across all the renewable energy zones, or was it for one?
No, this is for whole southeastern Australia.
All southeastern Australia.
Yeah, so yeah, definitely we could do for the renewable energy zones only as well. We have this mask for different renewable energy zones, and yeah, we'd be interested to have a look how these things varies if we do for the renewable energy zones rather than doing for the whole southeastern Australia.
Yeah, and so the hydrological drought was for all of southeastern Australia
Yes,
too,
yes.
Not just the regions where
No.
there's hydro.
No.
Yeah, cool. Okay. Awesome, thank you.
Awesome. All right, we might move on because
Sorry.
Look into process-based understanding with Michael's weather regimes and also the ETH weather objects. And we're going to show you a bunch of different things, and I hope you will find it interesting. Go on. So to begin, I focus on using Era 5 data, which I have some issues with in terms of the resolution, and I could talk about that for 20 minutes, but nobody wants that. So on the top here we have the percentiles of the actual wind through the entire annual cycle daily, and as you can see in the autumn months is when we see these wind thresholds for different percentiles at their lowest levels, which means we would expect periods of the least wind to be maximized in the autumn months. And then down here on the bottom, this is a bit more analysis just in terms of the climatology of all of the days, which we have decided on this wind drought from the capacity factor. All of the days where you would expect wind drought to be happening, and you can see that that's maximized on the east coast along the coastal and mountainous regions. And we're going to continue focusing on this southeastern Australia region for most of the rest of our analysis. I have one more figure, that's sorry. So this is just validating this upper section with the Quentin's analysis there on the bottom right, showing that we would expect the largest percentage throughout the year of wind droughts to be occurring in the autumn, so that's quite nice.
So it's continuing to look at this Southeast Australia region, we'll have a look at the synoptic weather types. So broadly speaking, these are describing or categorizing the weather patterns that we have over Australia. But do they actually have an impact on wind energy droughts? So what this plot shows here is the frequency of synoptic weather types, so how often they occur over the year in this region, and how they contribute to the droughts in this region, I should say. So what we see is a big standout here. So things above this diagonal are weather types that contribute more to droughts or occur more often when there is a drought. And we see this THA weather type has a very big standout, clearly has a lot more droughts in this time. So what is the THA type? It's Tasman high, and we can see these highs over Australia, something that looks like this. So this is an actual day that is categorized as that Tasman high A type. And when we have a look at how this relates to the wind droughts, here we can see the map of Australia and the anomaly of wind droughts. So how, if wind droughts occur more often or less often under this particular weather type compared to normal. And we can see quite like dark red colours across the Southeast Australia portion. So we can see that there certainly appears to be more wind droughts occurring under this Tasman high type rather than under other conditions.
So now we're going to look a little bit at the wind droughts during El Niño Southern Oscillation. So here is a map of wind drought frequency anomaly compared to the climatology side ends of phases. So the most interesting part is that we have more wind droughts during El Niño in the southeastern, especially exactly where there is all the wind turbines. And during La Nina, we would expect the opposite signal, but actually we also have pretty much a neutral or a little bit more wind droughts than usual during La Nina as well. And so the best case scenario is a neutral condition. And the El Nino have more wind drought because there is higher wind drought frequency during El Nino, mostly because there is more occurrence of high pressure weather regimes in the southern region in winter, spring, and summer. And next, in winter, it's especially a central high of type A and a flanking high of type C that drives these wind droughts in
spring, it's more the western high of type A, and again the Tasman high of type A that causes
Quack.
this wind drought.
Quack, quack.
And,
I stopped.
and yeah, in summer it's the same. It's also the Tasman high of type A.
Now, if you look at how weather regimes are associated with wind droughts, and we wanted to zoom in a little bit and look at the finer scale weather objects and how they contribute to wind power drought. And again, we see anticyclone here are one of the strongest contributor of wind droughts and also front depth as well. And they are like 2 to 3 times more than the other weather objects. And if we look closer into the anticyclone, it's more concentrated in the Southeast Australian region, which is also the Tasman High region, aligning with what our findings from the weather regimes. And the other 2 weather objects, cyclones and one conveyor belt, also contribute a substantial amount to wind drought as well. And next we're gonna.
I guess here what we want to say is that a large weather objects can contribute to wind drought, and it's important for us to understand and where do they contribute to the wind droughts. And we also want to understand how do they contribute to the wind drought, because the wind drought we define here is according to wind capacity factor. It includes the low wind and also the high wind. And then we dig into the cyclone in the northern regions. We find that the cyclone in the northern region contribute a lot to the wind drought days. And we know cyclone in the northern region sometimes include really strong tropical cyclones. Sometimes when the tropical cyclone is quite strong, and it might lead to the strong wind, which might break these the machines and this stuff. And we want to know these cyclones that contribute to wind drought, what's the wind speed for them? Is the high wind contribute to the wind drought or the low wind? And then this plot shows like overall the average speed of the cyclones contribute to wind drought are low winds. But we also, in our data set, we also find some high winds that contribute to the wind drought. So I think not just the wind, we prove not just the weather object important for the wind drought contribution, but it's also important to understand what's the wind speed of this weather object contribute to. That's it. And there's some summaries. Yes, and hopefully, apparently we have the Tasman High in Sunday, so let's look forward to that.
Any questions?
So, in terms of the contribution for the cyclone, is it cyclone only, or is the cyclone co-occur with other weather objects?
It was called cyclone and it's co-occur with other objects.
Okay, so all the contribution from cyclone and also the combination of cyclone and other.
Oh my goodness. Loads of questions. We're going to go to that table because we're going to take questions. Yeah.
Do you think the THA weather type is a reliable proxy for preparing for droughts? As in, should Energy Australia start caring about the weather types?
Oh yeah, I think that it definitely should. I think it nicely shows that more than half of the THA end up in wind droughts, so it's definitely important to look at the weather regimes, and it also depends on the season and everything, so definitely.
Alright, I'm going to move us on now to the next presentation. Thank you.
Solution to weather variability in renewable energy is battery storage. But here's the catch. Those batteries are largely charged by solar. So if we have 4 days of no sun, we're not only losing generation, but we're also draining the backup too. So this is the issue that we focused on this past week, and let's delve into the methods. We used 10 years of satellite data across renewable energy zones in the NEM
and calculated the clear sky index by taking solar panels, what's on the panels actually generated by divided by what they would have generated on an ideal day with no clouds. And then you get a number between 0 and 1, 1 being clear sky and 0 being fully overcast. We then defined a solar lull as anything below a CSI of 0.5, with one day having low risk, 2 to 3 days being medium risk, and 4 or more days high risk. And that left us with one question. Are these lulls random or do they coincide with Michael Barnes's synoptic weather types?
Okay, so firstly we want to understand what events were most common and in which regions they were most common. So we found that the low solar risk events were the most common and they occurred the most in Victoria and Tasmania. However, when we looked at the medium and high risk solar events on the same scale, we couldn't actually identify any trends with them. And so we looked at just the high risk events. And from that, we saw that the spread actually continued up to Queensland. So they weren't just most popular in Victoria and Tasmania, like the low risk, but also were most popular in Queensland as well. However, this didn't tell us on which time frame they actually occurred. And so we split it up into seasons, which showed that during the summer months, they occurred the most, high risk events occurred the most in Queensland, whereas in the winter and spring months, high risk events occurred the most in Victoria and Tasmania.
So this figure shows the most common synoptic weather types associated with high-risk solar events in each Australian state and season. The color indicates the synoptic weather type, and the percentage obviously show the proportion of high-risk events associated with those specific synoptic weather types. And so several broad patterns emerge here, and we can see obviously that in summer the monsoon drives the high-risk events because where there is convection, it drives clouds. And on the other hand, we can see that in winter and spring, cutoff flows are more frequent across each state, and they come with fronts, rainfall, but also extensive cloud cover, which can significantly reduce solar generation. And we also see some central highs in eastern Australia, which are high pressure systems that drive most onshore eastern flow and increased cloudiness. So here the key result is that although we can see a few correlation, most individual synoptic weather types account for only a very small fraction of those high risk events, which is typically around or even less than 20%. And they can account for large-scale atmospheric environments, but not for solar events on their own. And this can be explained because we focused with 850 hectopascal wind patterns, which are not specifically designed for solar applications. And when we compare this with short duration events, we can see different patterns, and it is mostly associated with western highs, which come with fast-moving systems, and they do not stall like cutoff flows might, and therefore they do not account for long-duration solar load.
Okay, so I've just got some key takeaways here and conclusions. So we've approached solar lulls from the perspective of duration, not just darkness. So on a cloudy day, it might be one cloudy day might be manageable for the grid, but 4 or more days in a row might be when the potential storage that we have empties and the firming generation will kick in and carry the grid. So for long durations events in the summer, the risk is lying up north in Queensland, but in winter it moves down to Victoria and Tasmania. So for our results, a 4+ day lull in these winter cases occur when a weather system stalls, such as a cut-off low in winter in Victoria. And these signatures could potentially, be used to forecast several days prior, offering opportunity for better price forecasting or even for network management. So yeah, that's it.
Questions?
It was like nice to sort of see that that finding about the slow moving weather systems. It's something a lot of people discussed this week, and that's quite important. Based off how often you found that was the contributing factor, do you think also that some events could be caused by sort of two different weather systems that coincide back to back on different days? Or do you think it's always the one slow moving weather system?
I think that would probably need to require more. We didn't really look into that, but we thought we discussed maybe, I think.
We made the same graph, but for the second most common. So we can probably show it. I don't know. That one.
Yeah.
Yes. Where you can see. And it's mostly again western highs and center highs and curve lows.
Thanks.
Any other questions? Awesome. Oh, there is one. Oh, sorry. I didn't see behind me.
I think I missed this at the start. The walls on the map, are they like the renewable energy zones, or how are they? Yeah.
That's great. Thanks.
What are we looking at here? Unless you're trained in meteorology, you can't really look at a map like this and say where the clear skies are, where the clouds are, and how those weather systems might be changing over the day. My group was interested in those weather changes, and we looked at 4 main types of weather and classified them as distinct objects. We looked at cyclones, fronts, and warm conveyor belts, which brought in clouds and rain and wind, and anticyclones, this big object, which brings clear skies and low winds. And we tracked these objects over the day, over many years, and how they covered and crossed the states to see how they impacted energy demand.
I'll just speak that. I'll pass it over to Sybil now. Thanks, Cindy. So essentially what we're trying to do here is understand how those weather objects then relate to energy demand in each state. And we've done this in 2 ways, by looking at daily changes and by looking at sub-daily changes. So we'll start off touching on these daily changes, where we've picked out 2 key states, one to look at the northern part of Australia, which is Queensland, and one to look at the southern part of Australia. Here we've looked at Victoria, and specifically Victoria during winter. So what we're showing in this map is of every day where demand in winter across a reference period of 2010 to 2016, where energy demand is higher, falling in that top 25%, what weather objects are occurring. And what we found was that on those days when energy demand was quite high, there was an above average presence of anticyclones. And that was the most noticeable trend against all of the different weather objects that we looked at. And if we have a look at the temperature and the wind on high energy demand days, we can start to understand these trends. As we can see, these southerly winds, which are anomalously southerly winds compared to the normal climatology in this period, and lower than normal temperatures as well on those high demand days. Now, if you flip your mind from the southern part of Australia up to Queensland, and we go to our next one, what we found was on these high energy demand days in Queensland, instead we had an above average presence of cyclones, but also a below average presence of anticyclones. And in addition to the cyclones, we saw things like warm conveyor belt inflow, as well as fronts at multiple different levels at the same time. And looking at our maps of the wind and temperature anomalies, we see these westerly winds blowing across toward Queensland, toward our major population centres, and we also see above average temperatures during summer on high energy demand days.
So we not only care about the long trend of daily anomaly, and we also care about the hourly demand anomaly.
So what Emma do is she look at the demand anomaly in different states, and when there is cyclone, warm conveyor belt, and anticyclone. So what we find here is when there is a cyclone and warm conveyor belt, which means the bad weather, the demand increase during these days. And that's because during those bad weather days, we tend to stay at home. So it's like a couch potato, stay at home. So there are lots of energy demand increase. And if we shift to anticyclone, which means a nice sunny day, and where are you guys? Apparently the beach, right? So we change to beach potato, and energy demand decrease during those nice sunny days. Yeah, so what Emma look at is the weather system across the whole states, and I really want to focus on just along the coastline where people live, and to see when weather system across those small area how energy demand change in the day. So here is the blue lines is the neutral day, which means there's no weather system, and the orange line is the day with bronze come between 7 and 9. And we can see that for all of the seasons, the energy demand increase across all the day. So it means like when there's front day, it will change the temperature, and then the demand increase when there's demand, when there's front. Yep. So the main takeaway here is if you can't remember any of what we say, just remember my beach potato and couch potato, because weather is really important for human behavior, and human behavior changes the energy demand in Australia. So I think it's very important for energy company to understand the weather and then to make a smarter decision in generating energy and also bad energy. Yeah. Thanks.
Yeah, I think that's a really nice finding. We did see like from your plot how weather system can influence the demand, but how can we actually make use of the knowledge? Like, is the relationship very general, very similar, so we can apply to like the company how they think about weather influencing demand?
I think it's kind of so we have weather prediction, right? So I think if we also have like real time the weather objects, and then we can, for example, if there's a front in the following hours, and then probably we will predict there will be an increase of the demand, and then the price of the energy probably increase, and then I don't know how would they deal with this kind of knowledge, but is that important? Like the energy company like to know like the increase of the decrease of the demand. Yeah, I think it's after a bit of research with energy company, I think we will know more better about that. So Ian, you had a question?
Yeah, Sybil, can you create a potato for every synoptic weather type?
Yeah, I think so.
How many synoptic types are there, Michael? 30 potatoes.
These are the weather objects, not the synoptic weather types.
What was that?
These are weather objects, so
That's
another.
okay. I want barn potatoes.
Yeah, I have lots of potato in my life.
Alright, Mulak has a question.
Yes, I just have a quick question. Like you have let's say windy and rainy day, and he says that people will be sitting in their home and also using but they also use the heating capacity. On the other day, when it's a sunny day, it's very hot, people will used to go to the beach and also want to use the the cooling fans or whatever it is. So how can you like sort of model the human behavior? Because do we have any idea that what people gonna do much more things like gonna be going to the beach or using much more resources back in their home?
Yeah, I think on the one hand it depends on the states. For example, if it's a nice sunny day in Victoria, then people really like go to the beach but still don't need to turn on the AC because it's not hot enough. But for Queensland, for example, if it's hotter than usual, and because it's
like in average, the temperature is high. So when it's hotter than average, then people probably turn on the AC a lot more compared with Victoria. So what we do at the moment is to find the most significant result. And for example, the impact of front in other states is probably not as obvious as in Queensland, but in other states there will be other weather objects which leads to more different impact in the energy demand. Yeah.
I think we can only get so far with assumptions about human behaviour, and we're also limited by the fact that the demand data is on a state-by-state basis, so we don't know where that demand is changing within the state.
I can see Sherry has a follow-up. Yeah.
I'm curious about really bad weather days, like tropical cyclone, really strong tropical cyclones. It might have a more impactful. For example, like the tropical cyclone Alfred, and when it comes to the coast, it's not just people can't go to the beach. It's like it destroyed the beach, and so the following weeks people can't go to the beach.
I think for that it needs more case study instead of this long-term trend, long-term average.
Yeah.
If there's like extreme cyclone, it destroy everything, then it definitely has different impact in energy demand compared with you just look at the long-term trend.
Sorry, I just want to make a comment.
You have a comment, Amy?
Yeah, it's really complex. Behaviour and demand is super complex. We had an honours student looking at this, and she was looking at public holidays and different places across Sydney. Depends on socioeconomic demographic. It depends on a whole bunch of factors, and it's not simple at all.
And the weather.
And in fact, the weather is a very low driver of human behaviour in terms of going places. It's more around energy demand. Just it's cold, therefore heating is turned on everywhere, or it's hot, therefore air conditioning is turned on. It's really complicated.
Yeah, and it's interesting when I plot a bit of figure about the energy demand in weekday and weekend, and like I find on the weekend the demand decrease a lot, which means people probably just go out and don't stay at home, and then the energy demand decrease a lot compared with weekdays.
All right, let's complicate things even more and thank this group. But now let's
I'm not going to
projector.
Oh, project. Okay. I can project. Can people at the back hear me? Okay.
Just speak up.
Speak up.
And look forwards.
So much to focus on. Oh my gosh. Okay. Okay. Is this a good volume? Not a good volume.
More.
More.
Maybe you should use the mic.
I'm going to restart your timer. It's going to be quick.
Sorry. Thank you. Okay. Oh, it's good. Yeah. Good. Okay. All right. So our group has been investigating how urban climate influences energy demand. Thanks for the introduction, Lisa. This is most of our group. Some people are away today, but we all did a great job, I think. Okay, so what do we know about urban climate and energy demand? We know that, as the previous group demonstrated, that the weather has an influence on energy demand, and we also know that the effects of urban areas influence climate variables. So what we wanted to do in this project is to understand, can we take in weather data for urban and non-urban areas and compare how that influences predictions of energy demand. Next slide, please. Okay, great. So this is our input data that we used for our model. So we had the Access RAM 3 weather data. We took a population-weighted spatial average at hourly resolution. And for these runs, we had two sets of Access RAM data, one with urban climate, or one with urban infrastructure, and one without urban infrastructure. So one city and one trees, essentially. We also had the AMO energy demand data, which is the total energy demand aggregated across New South Wales, also at hourly resolution. So these were our inputs to our energy demand model. Okay, so
we wanted to train our energy demand model using a machine learning method, and what is exciting is that we used a model that so far, as we know, hasn't ever been used before. So what we did, we took our urban access RAM data, so that's the one with the city included, and we also fed in our AMO energy demand data into an attention mechanism deep learning model, and we don't think this has been done before with weather data. So that's why there's a question mark, because we need to check some more literature, but we think it's new. Okay, and then we were able to train this model on the urban data and get predictions of the hourly energy demand compared that to the AMO energy demand data, so our ground truth. Okay, so how well does our model perform? So what we have here is the urban hourly New South Wales summer energy demand in our model, which is in the red, compared to the ground truth, which is the AMO data. This is over the training period of our model, and we can see that our model follows the ups and downs of the energy demand pretty well, which is what you'd expect because that's the training period. But what about if we look in the test period? Next slide, please. Yes, okay, awesome. So you can see the training data is there in grey still, but the test data is in the red at the end. And what's really cool is that in our test period, we can see that our model follows the AMO energy demand pretty closely. The root mean square error that we find in our test period is 590 gigawatts. I don't know what that means, but I'm sure Frankie can tell us what that means in terms of how many people's air conditioning that accounts for. But yeah, that's a great result. So we found that with this model, we were able to get this really close prediction of the AMO energy demand data in the test period. Next slide, please. Okay, and then we reran the model we applied the model to the no urban access RAM data. So we input the climate variables for a cityless world, I guess, and we could compare how this, we could work out how the energy demand predictions compared in this type of, with this input data compared to data with the urban effects. So again, what was really cool is that we saw that predictions with urban effects improve on predictions with non-urban effects. So this is the energy demand time series over the test data, over the test period, and you can see I've added our model with urban effects in red and the model without urban effects in green. And what you can see is that especially in the first part of the, just at the start of that time series, the non-urban effect doesn't capture that peak. And overall, the root mean square error increases by 13 gigawatts in that period. Okay, next slide, please. And again, what's really cool is that we see the urban hourly predictions capture the summer and winter diurnal cycles. So we saw in previous presentations that the diurnal demand profile is distinct between summer and winter. So broadly, in summer we get this one peak in the middle of the day, and in winter we get 2 peaks at the beginning and end of the day. So what's nice about that is our model follows the ground truth or the AMO energy demand data. Next slide, please. Okay, and also very excitingly, the model that we used, or the model that we developed rather, uses urban hourly predictions and it improves on recently published work. So Richardson et al. Recently published energy demand predictions using ERA 5 input data, which was aggregated daily and didn't have urban effects. And what we found is that if we include the urban effects and use hourly data rather than daily data, and then aggregate that up to daily energy demand, our model still follows the AMO demand data more closely than the Richardson model does. And that's all. Thank you.
Thanks. What's happening on the 24th of February? Why is the misprediction? What didn't go right that was meant to go right?
Oh, we used 20% of data for test
But if you go
For
back
testing?
to the time
Yeah, but if you go back to like your tests,
Yes.
yeah, so like 24th is completely out. So what was not predicted there that should have been predicted, or what happened on that day then?
We haven't been able to do analysis on like the exact differences for each day, but if you have the full summer period, you can see that most of the days are actually closer to that peak. So the fact that it's doing that peak probably means it's thinking that it's like those other days when there's some minor variation that it hasn't learnt.
Have you looked at which features of the model are doing most of the heavy lifting when it comes to these variables, and then potentially, I guess, similar to Michael, what features would then be most responsible for doing good or bad estimates of demand?
So features, do you mean the
The inputs into the model.
Yeah. Yeah, in the at the end slide. It was the time of day, I think, was the main feature.
Apparently the slide's not showing, but so time of day was one of the main predictors, and that was a proxy for human behavior. And then we also had, similar to what the previous group showed, we had that the B component of wind was a very significant factor, as well as the temperature and, to a very minor extent, precipitation and cloud. I think we also had one solar variable that showed up quite important, but that was with interaction with the temperature as well.
The solar variable.
Just on that, did humidity your
Yeah.
a measure of that didn't show up?
Humidity was sort of in the middle, but yeah, if we had the plot, it would be great. Unfortunately, it's not.
Have you looked at that slide? Is that what it is? In the meantime, Sam has a question, so maybe one.
Yeah, how much of the improvement in your model do you think is just due to having much higher resolution output that you're analyzing compared to Error 5? Can you comment on that at all?
So I don't know off the top of my head what the Error 5 resolution is. This model is only using the 12 kilometer, and we're hoping to do a 5 kilometer run to see how the resolution impacts. But our suspicion is that using hourly rather than daily is one of the main reasons that it's improving, and then the urban on top of that is sort of the next main factor.
That's okay, don't,
Sure.
I'm not gonna, we're running out of time. What I can suggest is, pop all of the slides, all of you, this is onto Cumulus, and including the secret hidden slides as well. And then you can have a look, and you perhaps talk to them, might be nice as well. Alright?
So we are using the same data as the group 7, and we're looking at whether city or urban has an influence on sea breeze and the capacity effect of the energy we can get from the wind. So I'll keep you in Sydney. So we're looking at Sydney, the same areas where they're looking at. So this is Sydney. We're using the high resolution, which is 1 kilometer resolution, of 3 months run for the models we're working on, where we're looking at both summer and winter, and both urban and non-urban areas. I mean, if there's city and there's no city in Sydney, and how the wind pans out, the wind energy pans out, if there's city or there's no city for the area of region we're looking at. So the first plot you can see here is the hour of maximum sea breeze frequency. And what to look at here is the spatial diurnal migration of wind, sea breeze in particular, and how it varies at space with diurnal cycle of the entire day. So you can see here from the arrows here that it starts off during the night at around 12 o'clock out at sea, and then reaches along the coast. This is the peak or the maximum breeze frequency, right? And it reaches the coastal areas around 12 o'clock midday, and then goes up to the land during the late in the evening and during the night. So you can see like the pattern of where the maximum frequency of sea breeze diurnally for the entire space of Sydney region. So with that, we're saying, okay, we try and look at the frequency and the capacity factor of that frequency for both control and urban together.
when you find that there's not much difference, so we minus out the control, the non-urban from the control, and this is what we get. And you can see here on the summer plot here for Sydney that during this period, I mean the difference we get, the anomalies, we can see that because of the presence of Sydney cities along the coast, the ocean capacity factors increases or intensifies for this plot here, which is it intensifies the capacity factor of Sydney regions, which is you can get high capacity factor for the ocean than the land, and that is because we said it's due to the urban heat, whatever the name is, like because of the heat island. That's the thing. It's not my thing, so no one. So that's So with the presence of the city, you got like intensification of the capacity factor out in the ocean, and because of that urban heat factor, whatever it is. So with that, we're saying, okay, we have to look at the wind profile of that for each of, for the space, the region of Sydney, and this gives us the different space and their profile for the wind profile for each of the clusters that we've got. So we cluster them together into different regions and plot the wind profile of each of these clusters. And this gives us the different profile, which you can see at the bottom, like for the coastal and the land. And what we can see from here is for both coastal, which is obviously sea and ocean, because of least resistance from the surface, you can get really strong wind. And you can see from the profile here, that the wind is really strong from the ocean. But from the land, it's different. It's a lot less strong wind from on land because of the presence of the resistance, the friction from the bottom, from the surface or the land, you can say. And that can also tell us the presence of buildings and stuff that reduces the wind. And you can see from the land wind profile as well. And from this figure, so you can tell where we can get the maximum wind at 160 meter height on the plot to the right. That we get the maximum wind at 160 meter height at different at spatial region here. So and the diurnal cycle. So with you get the maximum wind at that height for different regions. So at around 1800, which is late into the evening, you can get really strong wind at the top on land. But then you can get the strong wind out at sea during early during the night as well, which is tells of the same thing we've discovered on the first few plots, that tells of the diurnal cycle of these wind patterns and stuff. And the only thing we found, the thing we found also is that these patterns, can you go back a bit? This pattern only can be seen during summer, but not so much during winter, which is why we put the last figure is just, you cannot really see the pattern here during winter. But all the patterns I've talked about, you can only find that during summer, the Sydney region.
Question. Oh, I can see one behind me. Yes. I wanted to ask about the when you had the two figures of the capacity factor. Yes. Yes. So the positive in summer, the positive capacity factor over the ocean. That's what's that?
Well, that one is actually a very interesting thing. We use control run, which is the real city there. Sydney is over there, and the minus the one without really remove the city. So that's the difference. And that means if city is over there, that increase the sea break in summer from the ocean.
So that means you take out the non-urban from the control, which is the urban. That is which means like with the presence of urban, that influences the capacity factor, increases or intensifies the capacity factor.
On the same point.
Yeah.
Do you have any hypotheses on what the physical processes involved in that increase are? Because that extends quite far away from the coast. I don't understand how the lack of the sea makes that much difference that far out to the sea.
Yes, although I'm not an expert about the urban, but thanks for Matt to give us a very good lecture at the first day. So he showed us a line about the dual cycle of the city heat island, and you can see the city is not always during the whole day. The city is not always have a higher temperature than the area, so it will peak around the afternoon. So I think because we didn't show the time, we only show the average stuff. So yeah, I think the hypothesis is just the heat island time is longer than the time that is not that long, that high temperature. So I think that's why.
Probably was saying that there's an impact from the heat island, whatever it is, from the city that really influences what happens outside there. It sort of like blocks off most of the wind and stuff that comes in, so you got like.
You could think of it as an intensification of the same mechanism with the land sea breeze. So you get that mechanism occurring because it's the difference between the ocean and the land temperature. If the urban area is much hotter, that could intensify that same process at certain times of the day. Yeah. Whether it's it doesn't look like it's extending very far away from the city. So we would like to take a longer period to analyse this over, but it's an interesting preliminary result.
I was curious, do you see this same thing versus with the one from the model?
Yes, we use all of the plots from one plot.
Yeah, did you see this effect in the course or is it only in the higher resolution?
I think we do. Yeah, for
5 kilometers. Yeah. We did 5 kilometers, so 1 kilometer and 11.1 kilometers. And compared all together, no, there were no significant differences.
Thank you.
All right. Thank you.
So much can be achieved in like this short period is really amazing. And I can see the effort as well. I can see how you guys can try to condense everything you have found in like 5 minutes, which is pretty hard. So I try to make it short as well, maybe 5 minutes. You can start the timer.
You asked for it.
Yeah, so I think they're all very interesting and have a lot of potential research here. I can see, and because I can see a lot of interesting topic here that can relate to the energy industry a lot, and bear in mind that when we do the research, I think it's very hard to start. Sometimes you need to do the scoping. How should we do definition? For example, how do you define wind draft? How do you define the time series? And you guys mentioned about the data set as well. So which data set should I use? The spatial things. So a lot of these things it's hard to start. So when you have this kind of question, I think it's easier to just maybe look into the energy market. So what can that impact the energy market? So for energy market, you look into megawatt, you look into the price, you look into the demand, and if you think you can't understand how you change wind speed, which spatial things you can you should look at. Maybe just try to think about how can we try to convert the wind speed data into megawatts, and how can we actually simulate some kind of, for example, generation shortage period, things like that. So we talk about compound impacts of solar and wind. Do we actually look into the peak demand period? Because that's the period that we actually more interested in, because the industry always thinking about, when the demand is high and there's no wind, no solar, then there will be some unserved energy, so there may be load shedding and things like that. But this issue doesn't actually that serious, maybe overnight. So, or actually maybe it's not that serious in the middle of the day. But at around, for example, 5 p.m., 6 p.m., 7 p.m.ish, the demand is high, then we actually really want to understand, for example, will the wind draft actually will coincident in that timing, and then the solar drop, cloud cover, whatever, and then will impact the demand supply balance into the level that can impact the customer. So what I'm trying to say is all this research is very good. I think there's a lot of potential. Maybe we can actually further dive into it and then try to relay that into the energy industry a little bit more, and then that will be very awesome. And I think we talk about a lot of, and one of the things that we look into, like the regime, the climate, I think it's a very interesting topic. We look into that as well, and then we can't find very clear wind draft relation with El Nino. Maybe we are just, because I'm pretty bad at it, I just maybe ask the AI and then try to look into it, and then that's actually not a great way, but that's a lot of the professional in the industry is doing that. So that's why we need you guys. So we need you guys to try to understand the weather and then tell us, this year is going to be a super El Nino year. Are we actually facing some kind of like wind draft? And what is the impact? What's the duration? What's the timing? Does it affect summer? Does it affect winter? And all these kind of questions is what we actually want to answer. And then the last things I think another thing I can think about is about the sea breeze. It's a very interesting topic that we always want to time the sea breeze. It's just because always the sea breeze is something that can reduce the demand over the heat wave. So for example, when there's a heat wave of consecutive days, and then we want to understand whether the wind will come in at the evening peak or after the evening peak or before it. So that's really matter. If the sea breeze comes in like 4 p.m., then the demand will drop. Then we can't see the high demand, and then the price will be low. But if the sea breeze actually comes after the peak, at 7 p.m., 8 p.m., then you have the high prices. So as an energy participant, we really care about the prices as well. So if we can time the sea breeze very well, then actually it's like a very is an edge for us to try to compete with other participants. And I can understand like this is like one special cases, but but all this actually is like I think doing all this is just try to understand the weather system a bit more. How can that related to the industry, and then all those data back you up to try to give you evidence to understand the weather. And then because when we do the modeling, there's a lot of different reference year. We don't know which one to pick. And then to decide which one to pick, I think we should actually understand the fundamental, try to understand how the weather system can impact demand, can impact wind, can impact solar. Then that can help us to, when we do the modeling, and then to make the decision, choose the right reference year, and then maybe do the right decision to, for example, do we want to generate, do we want to go short in the position, go long in the position, and things like that. That's all I want to say. Thank you.